Yeah. Can you try talking again? Hello.
Everything's coming out really slow. Is it working okay now?
Yeah, can you hear us?
Yeah, I can hear you.
Yeah, our internet's pretty bad, but it's like about the same as last time.
If only someone could have predicted
The last
that.
spots.
Oh,
Yeah, but I think it's hooked up correctly this side, so that's good.
should we
Hey,
turn
well,
on the camera on the laptop? Do you think that will help at all?
no, it's just the internet.
Okay.
I use my hotspot. I have like tons of data, like 10 gigabytes. I don't know how much data.
That's the deal with that. Cool. Well, good luck.
All right.
Trying to think of anything else.
All right. Well, I guess I'll get started. William, you'll just have to let me know if I cut out because I have no way of knowing what's happening on your end.
I don't know why it's small. It gets small to like make the evidence there. Oh, okay.
Like I said, the volume.
Oh, the volume.
Is this? Is this here, but this microphone volume? Or program volume?
Yeah.
Which one?
Hey, Adina, can you talk again?
Yeah. Can you guys hear me okay?
Yeah.
Okay.
All right, she's gonna try. Good luck.
Thanks, Terry. Thanks, William. All right. Good morning, everybody. Welcome back to Math 127. We have been having some Marcus internet issues. So hopefully things keep going, but William will either let me know or text me if I cut out so that we can repeat things. A couple quick announcements before we get started. I'm going to do a quick share screen of Moodle just to remind you of a few things coming up. So first, I want to remind you that drop-in help starts today. So you can see on the schedule here which TAs will be in the drop-in help center. So if you find someone that you enjoy working with, you can see when else they're working. This may change a little bit this week, but this is essentially who's going to be there during what times. Wednesday is a Monday schedule, so my office hours are a little wonky because I have a meeting in the middle of the day, so I'm changing them. On Wednesday, I'll be there from 9 to 10, and I can also meet with people later in the day if you need. So I mentioned in my last email, there's going to be some algebra workshop reviews this week, one on Wednesday and one on Thursday. So if you haven't already had a chance, please make sure you look at the algebra assessment. And if you don't know how to do many of them,
You actually cut out. Can you repeat the last minute? We lost you for about a minute.
Yes. So there's going to be workshops this week on Wednesday and Thursday. based on this algebra assessment. So if you don't know how to do some of the problems, you should stop by and make sure you get caught up on that early so that when the algebra comes back later in the course, you know how to do that. Both the Wednesday and Thursday session will be the same, so you don't need to go to both. I also want you to know, I mentioned this last time, but I did figure out how to live stream this session on YouTube. And so if you can't come to class one day for any reason, you can click on the live stream link during the class session and watch the session live from wherever you're at. I tested it out in the class before this, and the live stream went really well, better, I think, than the picture in Marcus. So if you have to be absent, but you're able to watch from a different location, you can use the live stream link. And if you are sick and you can't watch during real time, there's an asynchronous lecture for each of the things we cover. So you can always watch that either ahead of time or when you're feeling better if you are unable to attend class. The other thing I want to mention is that your first set of mini quizzes are due this week. So you'll see them right on Moodle. When you're ready to take them, you're just going to click on it and you'll have 15 minutes to complete it. And again, there's only 3 questions. This is meant to be a low stakes assessment. So we used to have a lot of high stakes tests in this class, which we didn't really love. But given the pandemic, we were able to change our assessment structure. And it makes it so that all of them are pretty low stakes. So there's 21 mini quizzes throughout the course. So if you don't do well on a couple of them, it's not going to be a big deal. So when you click on it, you have 15 minutes. Unless you're a student who gets extended time, you'll see that that says 30 minutes. And you have to complete that by Wednesday at essentially midnight. So it's just 15 minutes that you need to find. And I would recommend trying out some of the homework before you do the mini quiz, just so that you can get some practice in doing some of the problems. Okay, the second mini quiz will be due on Sunday. So you can see that down here, as well as the first homeworks for the week, which are on 1.1 and 1.3. As I mentioned before, I strongly recommend that you schedule time to work on your homework when there is drop-in help available, which most days is 2 to 9, just so that if you get stuck on a problem, you can pop in real quick and get some help. Okay, so that's just sort of the brief announcements here. We are going to be picking up where we left off last time. We're going to be finishing up 1.1 today. What is a function? And as a reminder, 1.1 is just a lot of terminology so that we're on the same page about how to talk about different things in mathematics. Okay, so I'm going to switch over to my doc cam. I did get a new doc cam over the weekend, which I think is a little clearer, although, let's see, I gotta hit the autofocus button once here. The graphs are still a little light. I am going to be ordering a new printer to see if that will help, but it may take about a week to get here. So when we talk about graphs, if it's important that you know the values, I will draw them in. So the next thing that we need to talk about, last time we talked about independent and dependent variables, inputs and outputs, and now we're going to be talking about discrete and continuous functions. So there's 2 types of functions when we talk about this particular type. A discrete function is defined for inputs that are listed, but nothing in between those numbers. So an example of a discrete function would be the number of children that somebody has, right? You can have 1 child, you can have 2 children, but you can't have 1.5 children, right? We don't accept numbers in between because it doesn't make sense in that context. So discrete functions take on very specific values and nothing in between. Continuous functions allow any possible number to be plugged in. So one common continuous function is when we talk about things that have to do with time. Typically, time is considered to be continuous because you could be doing hours, but between hours are minutes, and between minutes are seconds, and then you can divide seconds into nanoseconds, right? So you can plug in any value for time and it would make sense. So for continuous functions, we can plug in any type of number. So what we want to do is we want to be able to look at the functions we're working with and determine if they are continuous or discrete. So again, continuous, you can plug in any number of any type. Discrete functions, you can only plug in certain numbers. So we're going to start with two quick examples. We have a formula and a graph. Actually, maybe we'll get all three on the screen. A formula, a graph, and a table. So the numbers on the graph don't really matter. You can just see it's just sort of a wave here. All we're trying to do here is determine if each of these things would be considered continuous or discrete. So I want you to take 1 minute and jot down whether or not, or not, whether you think it's continuous or discrete for each of these three examples. So for the formula, for the graph, and for the table. So take a quick minute and jot down what you think it is. Feel free to check in with someone next to you, and then we'll go through them in approximately 1 minute. So just take a quick guess if you're not sure. All right, so let's go through and just check real quick. So for the first type, we have a formula. And here you'll notice that there's nothing here that prevents me from plugging in whatever I want. So I can plug in positive numbers, I can plug in negative numbers, I can plug in decimals, I could plug in pi. There's nothing preventing me from plugging in any number I want or any number in between. So this one is continuous. So I'm going to put a C for continuous. On the graph here, right, we just have a function that goes up and down, right? But what I notice is that I can pick any independent number on this axis, and there is a corresponding output. So if I wanted to pick 1.125, something obscure, right, there's going to be a Y value that comes out. So for this graph, where I see it, this function is continuous, okay? Now, we are going to define continuous much more rigorously later, but for now, we want to get sort of our internal reaction to be able to judge things quickly. Now, for the table, this one's a little tricky. So here, the only values that I know about are x equals 0, 2, 4, and 6. I don't have any information about what happens at 1. I don't have the information about what happens at 1.1, right? 1.5. And so if I don't know some specific way to get those values, then this function is going to be discrete, the way it's set up. Now, there's a caveat to this, because sometimes you will have a table that says, assume the function that generates this data is continuous. And what that would mean is that there are values for everything in between. We just don't know what they are. But unless it actually says that in the problem, then we have to assume that this is discrete, that the only values we can pick are 0, 2, 4, and 6, and that we are not allowed to pick anything in between unless there's some other information in the setup that says otherwise. So this table is going to be discrete. So typically, formulas are often continuous. The graphs that we look at are often continuous. And then the tables could go either way. It'll either say it's continuous in the setup, or we assume it's discrete. Now let's look at a word problem and try to determine if in the word problem, if the situation we are describing is something that is continuous or discrete. So take a minute to read this problem and then try to guess whether or not it is continuous or discrete. Okay, I'll give you 1 minute to look it over and make your guess. here, again, we're going back to this problem that we sort of talked about before, where we have an ice cream shop and our independent variable is T, the number of toppings. So the question is really, can I plug in any number into T and have it make sense? Or can I only plug in certain numbers? And so in this type of situation, much like the one with the number of children, only integer numbers really make sense, right? You can't have 1.5 toppings because as soon as you go past one topping, you have two toppings. There's nothing in between. So the only numbers we can plug in are things like 0, 1, 2, 3, 4, 5. So that makes this function discrete. So we don't even know what the values are per se, but we do know that it has to be discrete because the things that we plug into T don't include every single possible number, okay? So when we talk about continuous and discrete functions, again, I'm not going to ask you to define this on a multiple choice quiz, but later on we'll say this function is continuous or this function is discrete. And the idea is that you will understand what that means because we've refreshed on this, okay? So the next one that we're going to talk about, which is probably the thing that will come up most in all sorts of ways throughout the course, is domain and range. And I'm guessing all of you have heard these words before, but you may or may not remember what it is or how to find it depending on when you learned it, right? It might have been a while ago. So we want to make sure that we are on the same page about what these things mean. So the domain of a function is the set of all possible inputs for that function. So this can be defined by the function. So there may be things you can and can't plug in based on the function itself, or it may be that someone like me or the creator of a situation restricts the domain in the setup of a problem. So what does that mean? That means I might say, hey, what's going on with this function? But what's going on for x equals 0 to x equals 10, right? So I might tell you exactly where I want you to look and restrict the domain, but the function itself might also restrict the domain. A common example, okay, is the function 1 over x. So when you think about domain, you're thinking about what can I plug into this function and what can't I plug in? So I'm sure if I asked you what number should I not plug into this function, you would all figure out that it should be 0, right? So you can't plug 0 into this function because you can't divide by 0, right? What happens when we divide by 0, right? So black holes are created, people die, it's a mess, all that sort of stuff. Not really, but we can't do it because it's not defined. So we have this intuition that we know we're not supposed to divide by 0. So that's part of the domain. The domain for this particular function is everything but 0. We can plug in any other number, right? 1, 2, 3, -1. We can plug in fractions and decimals. That's all fine, but we can't plug in 0. So that's a situation where the function defines the domain because there's things and operations we can't do at particular points. Okay. Now, the range of a function is the set of outputs for a function. Okay. This comes while considering the domain. So if your domain is restricted by me or by a problem, that means that your range might also be impacted. Now, when we talk about the range of a function and the outputs, a common example that you may remember to help illustrate range is from the function x squared, okay? So the domain of x squared is all real numbers. You can plug in anything you want into x squared, no problem. The range, however, is going to be all non-negative numbers. So that means all the positive numbers plus 0. So we could get out 0, because if we plug in 0, we get out 0. And then we get positive numbers. You can't get a negative number from x squared. So the range here would be 0 to infinity, right? We don't have any negative numbers though. So again, the domain is the inputs and the range is the outputs, okay? So we're gonna practice a little bit on domain and range with our 4 types of functions. We're gonna start with our formula here. This is just a blank graph space in case you wanted to graph it. The graph's not actually there, but it's up to you. So we're going to consider the function we've been looking at, the formula here, x squared minus 2x minus 3. I want you to try to figure out what is the domain of this function. So what can you plug in? Is there anything you can't plug in? And what is the range of this function? The range is a little more tricky because we have to figure out what types of outputs we get from this function. This can be done by graphing it if you have a graphing calculator, or you could graph, by picking some points, or you can use algebra to find the vertices of the quadratic function. Either is fine, but the range is a little more tricky. So take 2 minutes and try to figure out the domain and range of this particular function. Feel free to check in with someone next to you, and in 2 minutes, we'll go through it together. So take about 30 more seconds to finish up whatever part you're working on. All right, so let's take a look at this. So for this function, we start by identifying the domain. I find it's typically easier to determine the range if you do the domain first, but there's nothing explicitly preventing you from doing it in the other order. So when I consider this function x squared minus 2x minus 3, there's nothing that I'm worried about plugging in, right? I can plug in 0, I can plug in 1, positive numbers, negative numbers, everything in between. So the domain here is going to be called all real numbers. And we're going to talk about the notation for this next, so don't worry about that right now. But we can plug in anything. So if your conclusion was, any values, all real numbers, if you already know the notation, if you use that, any sort of way of writing that, that's our domain, because we can plug in anything we want, and we see that the function will exist as we go from left to right. Now, the range is a little more tricky, okay? So the range here, we can see that this function goes up forever, right? As we plug in bigger and bigger values, right? If you plugged in 5, 10, 15, 20, you'll see that the values get higher and higher. So there's no upper bound to this function. However, we can see that there is a lower bound, right? So there's no values that are outputs that are below this particular value. So how do we determine this value? Well, like I said, one way is that you can graph it. You can graph this on your graphing calculator and calculate where the minimum is. You could plot some values till you try to figure out where that minimum is, or you can use the algebraic method of finding the axis of symmetry to determine where the vertice is. If it's been a while, I'll just remind you, you're going to do negative b over 2a to get the x value of this vertice, where b is going to be the number that's attached to the x. So the opposite of b here will be 2. And then my a here is 1. 2 divided by 2 is 1. So I know that my lowest vertice here is going to happen at x equals 1. And then to find the corresponding y value, I would plug it back into my function. So if I were to plug in a 1, I'd have 1 squared minus 2 times 1 minus 3. So that's going to give me negative 4. So this line right here is y equals negative 4. This is my vertice, which I said is 1, negative 4. So my range is going to go from negative 4 to infinity. Okay, so I can't go below negative 4, but starting at negative 4, including negative 4, and everything above is included for this function. And again, we're going to talk about how to formally write this using what's called interval notation in a minute. So if you wrote this already in interval notation, that's totally fine. But you should have something of the sense that all our outputs will be between negative 4 and infinity. Okay, so that's our range here for this particular function. So like I said, the next thing we need to talk about is how to write these intervals. So we're going to sort of take a sidestep, learn how to formally write these intervals, and then go back and do some more domain and range. Okay, so how we write the notation for our intervals depends on if we have a continuous or discrete function. We're going to start with the continuous case because that's what we just looked at. We looked at a function that was continuous, and that's broken up into two subsets, what's called a closed interval and an open interval. I'm going to tell you the difference before we write the notation. A closed interval includes the endpoints. An open interval does not include the endpoints. Most of the functions we look at, if the endpoint is a value, we have a closed interval. So there's two ways to write this, and this is sort of the general representation. The first way is by using less than or equal to symbols. So x is less or x is greater than or equal to a, but less than or equal to b. This is closed because of the inclusion of that or equals to. That means we can include the endpoints. The other way that we could write this same thing looks like this. Now, this is a notation that not everybody learns. So if this looks completely new to you, that's pretty common. Usually about 50% of people have seen it written this way. What this means is x is an element of, that's what that little symbol means. So it's in the interval a to b. And because we have brackets, we can include those endpoints. So for example, if you see something where in the setup, it says something like this, this means x is an element of the interval 1 to 6 that includes 1 and 6. So that means you could have an x value, any number between 1 and 6, including 1 and 6. Okay, and the way that we would write that with our other notation, looks like this, right? So those mean the same thing. So sometimes you'll see this written like this, but sometimes you'll see it with this notation here, okay? Now, an open interval means that we do not include the endpoints, and the notation for that means that we're going to have the less than and the greater than symbols without the equals to part. And the other notation, we're going to use open brackets. Okay, so those are parentheses. That means that we can pick any number between A and B, but we can't pick A and B. We can't use the endpoints. Okay, these we are always going to use when we're dealing with infinities. Okay, so if we were going to be talking about the range from the last problem, which was a little more interesting, okay, our range was from -4 to infinity. We can include the -4, but the infinity has an open bracket. That's how we would write this. The range is the outputs, so we use the y or the f of x. The 4 or the -4 is included, so we use brackets. And infinity always has an open bracket, okay? Infinity is not a number, it's a concept. And there could be a whole class on the philosophy of infinity, but you can't just plug infinity in. It's not a number, it's an idea. And so since it's not an actual number, infinity or negative infinity will always have open brackets. Okay, so that's an example of applying that notation. Okay. So we're going to practice a little bit more with our domain and range. I am going to draw on this graph to make it darker. This is 1, this is 2, -1, -2, this is 2, 4, 6, -2, -4, -6. So hopefully you can see that. So the problem here says, assuming that the entire function is pictured below, which means it doesn't go on past this, find the domain and range for this function. So I want you to take 2 minutes and jot down, trying to use the notation we just talked about, either the inequality signs or the brackets, the domain and range for this graph. Okay, and we'll be using X's and Y's here. Okay, so try jotting that down. Check in with someone next to you if you'd like. And in a minute or two, we'll go over it together. All right, take about 30 more seconds. All right, so let's take a look at this. So again, when determining domain and range, we start with domain typically, and the domain are the values that can be taken as inputs. So we're looking at the x-axis to determine what those will be. So here I can see that the last input here is -2. And then over here on the right, it goes up until 2. And there are values for -2 and 2. So I'm going to write this like this, but we could also write this like this. These mean the same thing. But our domain is going to be -2 to 2, and I should include those because they do have y values present there. The range for this function, okay, I'm going to look at what the output values are here on the top and on the bottom. So I can see that the highest value that I reach is 4, and that happens when x equals 0. And the lowest value is -4. So my range here is -4 to 4, or again, if I want to use my alternate notation, I could write it like this. Okay, so again, we're looking at what's happening in the picture to determine what our sort of max values are for both the domain and range. So we use this type of notation whenever we have continuous functions. But as we know from before, we also have discrete functions. So we need to talk about how we talk about and write domain and range when dealing with a discrete function. So we're going to start with an example from a table here. It says, assuming the entire function is represented below, find the domain and range for this function. So this is discrete because there's nothing to tell us otherwise. This is the whole function, these 4 values. And so we want to figure out how to write domain and range here. So the difference for discrete functions, okay, we'll do domain first. The first thing I want to note is that we're using the variable t because that's what's in the table. Okay, if it said x, we'd use x. So we still use this idea of is an element of, but now we're going to use curly brackets for discrete functions. And for discrete functions, what we do is we list the values with commas in between. So here we would have 0, 1, 2, 3. So these are the values that t can take on. And again, I got those directly from my table, 0, 1, 2, 3. So those are the domain numbers, and those are the inputs that I could choose to then work with my function. Okay, for the range, that's with the outputs. My outputs here are given as f of t, and I'm going to do the same thing. Okay, the range is going to be all the outputs I can get based on this function. So that's going to be -1, 1, 7, and 17. So the difference when we write the notation for domain and range with discrete functions is the curly brackets and the list, right? We list them all. Now, sometimes what we're going to find is it's not reasonable to list all the inputs and outputs, but we'll look at an example of this next. So this is the notation for a discrete function. We're going to use the curly brackets and the list, and we're going to label domain and range. Okay, so we're going to try this with a word problem, and we're going to see how we can make these lists for our domain and range. Okay, so here the cost of ice cream C in dollars at a local shop in Mathtown, Ohio is a function of the number of toppings T ordered to be put on the ice cream. So C is a function of T. Now we have some additional information. If the shop offers 10 different toppings and the cost of the ice cream is given by C equals 5 plus 0.25 T, what is the domain and range of this function? So I want you to take a minute and use our notation for discrete functions to think about how we would write the domain and range for this function. Okay, so I'll give you 1.5 to 2 minutes to try to jot that down. And then we'll go over it together. Okay, so take about 30 more seconds to finish up whatever part you're working on. All right, so here, when we're talking about domain, we're asking what values we can input. So that has to do with t, our independent variable, and toppings. So there's 10 different toppings. However, we could also choose to have no toppings. That's a reasonable assumption here. So my domain here is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, as you can imagine, writing out lists like this can get really arduous. So we wouldn't want to do this if we were talking about a discrete function that had, say, 100 choices, right? We're not going to want to write out 1 to 100. So one of the conventions we do is if you have a long list like this, you can write the first 3 numbers and then 3 ellipses and then the last number. The first 3 numbers tell us how to count. I can tell by the first 3 numbers that I'm counting by ones, so 0, 1, 2, and then I would go 3, 4, 5, 6, 7, and keep going until I get to 10. So when your lists are really long, right, you can use this notation to shorthand it so that you don't have to write out huge lists of numbers, okay? So in the last example, there were only 4, so that was fine. One of the differences with the last problem as well is that there wasn't a pattern. So we need to just take the numbers from the table. But since we have a function here that's going to dictate how these things are created, we can use our shorthand if there's a super long list. So the range here are the different costs that I get from this number of toppings. So if I have 0 toppings, my cost is $5. If I have 1 topping, my cost is $5.25. If I have 2 toppings, $5.50, right? Now, because I don't want to write out this whole list, I'm going to do 3 ellipses and then a comma, and then I'm going to jump to my last number, which is 10 toppings. If I plug a 10 in here, I get 5 plus $2.50. So I get $7.50, okay? So my range, I can see, is changing by 25 cents each time, all the way up to $7.50. So I'm using the shorthand notation here just because writing out that long list is pretty long, and this means the same thing. So that's how we use our discrete functions and how we talk about domain and range here. Again, a lot of this is terminology so that you recognize it later. So if you see something like this, you'd be you'd make the assumption that we have a discrete function and that we were talking about, domain and range because we see the curly brackets for a discrete function. Okay, so that's domain and range in a nutshell. The next sort of piece is a very just brief definition of what a mathematical model is. We talk about these a lot, and we are going to do a lot of modeling in this class. So this is the first time I'm going to talk a little bit about what's upcoming and what it's going to mean in terms of calculus. So a mathematical model is a description of a system or phenomena that is a real world situation using a function. So we could use a graph, an equation, a table, or a word problem, okay? When we talk about modeling, it's important because one of the things we're going to find is the most powerful aspect of calculus, which we'll be learning this term, is if we have a good model, we can use it to make predictions into the future, right? We're not mind readers. It's not like a psychic ability. We are using math to make a best guess about what will happen in the future. Why is this important? People use this in the stock markets. They use this for weather. We use this to figure out crises. One example is a BP oil spill many years ago. They were measuring how quickly the oil was coming out and how quickly the hole was changing to figure out how long they had until it became a crisis, till there was a certain amount of oil into the ocean. So being able to make these predictions is really, really powerful, and probably one of the main reasons you're required to take this course, because whatever your major is, they want you to be able to look at something and use it to make a pretty good guess or approximation about something that will happen later in time. It's a very powerful tool. But in order to get to the place where we can make predictions, we have to be comfortable looking at models and understanding what they mean before the prediction. So what we're going to do is we're going to look at a very simple model here. And we're going to just do a couple of the things we've talked about, use the terminology and the notation we've learned to make sure that we can just talk about this model with the things we've learned last class and today. So a popcorn vendor at Fenway sells popcorn for $6 a bag. Let R be the revenue in dollars for one night sales. So that's the amount of money you take in. And P represents the number of bags of popcorn sold. So the vendor's revenue for this can be modeled by R equals 6P. So here we're using R and P instead of X and Y. So what I want you to do is identify what is the independent and dependent variable, determine if this function is going to be continuous or discrete, and think about a way to represent the domain and range for this function. Okay, so take 2 minutes, see if you can jot down the answers to these 3 questions. Feel free to check in with someone next to you, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so here we want to identify the independent and dependent variable. Normally we're looking at things like X's and Y's, but we saw here that we have different letters representing our variables here. So we want to make sure we have them lined up correctly. So our independent variable is the one that we get to plug numbers into to get a dependent value. So my independent variable here is going to be P, the number of bags of popcorn. So that is the variable we're going to be plugging our inputs into. Our dependent variable in this model is R, the revenue, because the revenue depends on the number of bags of popcorn. Okay. So again, when you're identifying the independent and dependent variable, you want to make sure you're using the letters given in the scenario. Part 2 is to determine if this function is continuous or discrete. So again, whether it's continuous or discrete depends on the inputs, right? So that has to do with the independent variable. And the question is, can I input any type of number, or can I only input certain types of numbers? And so here, I can really only input certain types of numbers, which again are going to be integers, right? So I can put in a 0, a 1, a 2 bags of popcorn, 3 bags of popcorn. That all makes sense. But 1.5 bags of popcorn doesn't make sense, right? I can't buy 1.137 bags of popcorn. So here, this function is discrete, okay? Because again, the popcorn inputs can only be integer numbers. So now we want to talk about a way to represent the domain and range of this function. This one's a little tricky because we're missing a key piece of information to make this as exact as we would want to. We don't know if there's a limit on the number of bags of popcorn, right? So how do we deal with this? So popcorn, is an element of, so the number of bags of popcorn, I need to think about what the lower bound is. It doesn't make sense to have negative numbers. You can't buy -4 bags of popcorn, but I can have 0 bags of popcorn, right? Let's say the game is canceled and no one buys any popcorn, or people are boycotting popcorn for whatever reason. You could certainly sell 0 bags, right? You could sell 1, 2, right? Whole numbers are what we're looking for here. Now, because we don't have an upper limit, we put ... So that means it just keeps going. 0, 1, 2, 3, 4, 5, 6, 7. If we were to get additional information about the maximum number of bags, we could throw it in at the end. But since we don't, we leave it open-ended. And the assumption is that it just keeps going up until it doesn't, right? For our range, we're going to have revenue. And again, that's directly related to domain. So the amount of revenue we get if we sell 0 bags of popcorn, we do 6 times 0, which is $0. If we were to sell 1 bag of popcorn, 6 times 1, $6. If I were to sell 2 bags of popcorn, $12. There's no scenario in which my revenue would be $4.25. Right? Because that doesn't make sense with my domain. So again, because I don't know how many bags I can sell, I just do ... And I can see the pattern is that my outputs have to be multiples of 6 here. So we would write the range this way. So when we have real world models, they are not as exact as when we have other types of models, which is why we sometimes end up with these open-ended brackets here. Okay, so that's just a little glimpse at a model. Our next sort of terminology that we have to think about are going to be the intercepts of our functions. So oftentimes knowing where a function begins and where a function ends is helpful within a model. So the vertical intercept of a function is where our function will cross through the vertical axis or the y-axis, right? The one that goes up and down. Because we're dealing in functions, this will only happen one time. So there'll only be one vertical intercept for any function we are looking at. And this is going to specifically happen when your independent variable equals 0. So if we want to determine where it is, we need to figure out the dependent value when x equals 0. Horizontal intercepts happen when we cross through the horizontal or the independent axis. This can happen in multiple places. You can have one horizontal intercept, you can have 2, 3, 4, you could have none. Any of these are possible. So we need to make sure that we find them all when we're dealing with horizontal intercepts. And this specifically happens when the dependent value equals 0. So for both of these cases, we're letting something equal 0. It just depends on which intercept we're looking for. Okay, so what I'm going to have you try now is I want you to look at this particular formula. So this is the x squared minus 2x minus 3. It's the formula we've been looking at for our other examples. And I want you to determine the horizontal and vertical intercepts for this function. So where would this cross through the axes? So you can do this algebraically by plugging in either x equals 0 or y equals 0 and solving here. And you can also double check it by graphing it either on a graphing calculator or graphing it out to check your algebraic work. So I want you to take 2 minutes to think about this. I will tell you that the horizontal intercept is a little more work and there's more than one. Okay, so take 2 minutes, try it out. Feel free to check in with someone next to you, see if they're getting the same thing, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's start with the vertical intercept. We know by definition, this is going to happen when the independent variable equals 0. So this is a plug and chug situation. We're going to be plugging in a 0 for x. So we have 0 squared minus 2 times 0 minus 3. When we plug that in, we get a value of -3. So my vertical intercept, I'll write it over here, is going to be the point 0, -3. So we write this as a point, as you would identify a point on a graph of where it is. And when you do the vertical intercept, the x value is always going to be 0. And in case it's been a while, when you write a point, you always write the point x, y, or independent value, dependent value. So our vertical intercept here is 0, -3. That's where we're going to pass through that vertical line on our graph. For the horizontal intercept, remember that happens when the dependent value equals 0. So we're going to set 0 equal to x squared minus 2x minus 3. So that's a quadratic function and it equals 0. When you have a quadratic function equals 0, you have two options. You can factor it if you like factoring, or you can use the quadratic equation. You're going to get the same answer either way. I'm going to factor this just because we will be factoring later in the class, and this is a good time to go over that. So when you factor a function, you are looking for two numbers that multiply to give you the last number, but add up to give you the middle coefficient. So I'm looking for two numbers that multiply to give me -3, but add up to give me -2. So here I'm going to have a -3 and a +1. So -3 times +1 gives me the -3, and -3 plus 1 added together gives me the -2. So now I've factored this, and the beauty of factoring is we now take each factor and set it equal to 0. Okay, if x plus 1 equals 0, then x will have to equal -1. I just subtracted the 1 over. And so that gives me -1, 0 as my first horizontal intercept. But I also have my second factor, x minus 3 equals 0. If I solve that by bringing the 3 over, I get x equals 3. Now remember, for the horizontal intercept, the y value was 0. So once I've solved for x, I can write my points by just putting in the x value, 0. So here I have two horizontal intercepts and one vertical intercept. The best way to double check these is to graph the function and make sure that you're getting the same thing. This particular function is the one we did earlier, and I graphed it. So I'm just going to show you a picture of it real quick here. So we can see that that matches up, right? So this is 3, 0, -1, 0. Those are my horizontal intercepts. And then over here, I had 0, -3. That's my vertical intercept. So you could graph this function on your graphing calculator to make sure that your intercepts line up with what you're finding algebraically. Because again, if you find something algebraically and the graph sort of substantiates what you've done, there's a pretty good chance you've done it correctly. Okay, so let's take a look at horizontal and vertical intercepts on a graph. I know you can't see this too well, so I'm just going to kind of mark some things down and we'll do this one together. Let's start with the vertical intercept. We'll do that in red. So quite literally, we are looking for where we cross this axis. So that happens right here. This is the point where I cross through this vertical axis, and this happens at 0, 0. So my vertical intercept here is 0, 0. It's where my function crosses through this vertical axis. Now, you can see here that there's quite a few places where I'm going to cross through the horizontal axis. Right? I see 1, 2, 3, 4, 5 places that I cross through, which means that there's 5 horizontal intercepts. Okay, so remember, our horizontal intercepts all have a y value of 0. So I'm just going to write that in before I even look. Okay, all of these are going to have a y value of 0. So I need to approximate the x values from the graph. So this one down here, I know you can't see it as well, but I'm going to call that negative 6.5. If you have it printed out, you can probably see that pretty well. Over here, this is a little bit past 3. So I'm going to call this negative, I don't know, 3.2. You could call it negative 3.1. It's not directly on 3, but it's pretty close. And we want to get pretty good at just sort of approximating in general. Here, this goes right through the origin. So 0, 0, you'll notice, is both a horizontal and a vertical intercept. It's both. Over here, we'll call this 3.1 and maybe 6.3. Okay, so we have 5 of them. We are approximating. I know that some of you are probably panicking a little bit, like, what if I thought it was 3.2? That's totally fine. I just want to remind you that your assessments are all multiple choice, and it will be obvious what the correct answer is. So if I'm asking you about horizontal intercepts, there won't be one that says 3.1 and one that says 3.2, right? There'll be one that says something like 2.5, 3.1, or 4.5. So it'll be very obvious which one to pick. So when you're doing this on a graph, you are just finding where we cross through the two axes, okay? So we also want to be able to do this on a table as per usual. So the next example we're going to look at, we are going to look at this table here. I want you to take a quick minute and try to jot down where the vertical and horizontal intercepts would be on this table based on our definition about the zeros. All right, so remember, by definition, a vertical intercept will happen when the independent value equals 0. So we want to go up to our independent values, which is our top row, and see if any of them are 0. Fortunately, here we see that that happens in our first entry. So we are going to have a vertical intercept at 0, 30, okay? If we're looking at a table to try to determine horizontal intercepts, we want the dependent value to be 0. So we look through the bottom row of these dependent values and look over here, we find one down at the end. Remember, there can be multiple horizontal intercepts, so make sure that if you see more than 1 0 in that line, that you write them all down. So this is going to be 6, 0 as our horizontal intercept. Now, we don't really know what's going on with this function, but by definition, by identifying these zeros, we are able to figure out some information here. Okay, so that's how we would look at that on a table. We are going to make a quick jump. There's a word problem, well, 2 word problems here that you can practice on, but I want to make sure we get to the definition of increasing and decreasing functions, which is our last thing that you will need before your quiz. Okay. So you can try out those 2 word problems from before. We're going to jump ahead here to finish up on our 1.1. So the last bit of terminology here that we need is the terms increasing and decreasing functions. So an increasing function is said to be increasing if the values of the dependent variable increase as the values of the independent variable increase. Now, I really want to point out the last part of this definition. As the values of the independent variable increase. What does that mean? That means when we are looking at x values, that we are considering what happens when we read them from left to right, right? When you read a graph, you read it from left to right. I can't tell if on my video it's going from left to right or if it's mirrored, but from left to right. So the decreasing function definition is that those dependent values go down as the independent variable increases. So you see the word increase in both definitions because we are letting those x values go from left to right. And then we are looking at whether the dependent values go up or down. That's going to tell us what is increasing or decreasing. So when we think about this in terms of our formula, right here, where's my picture? Just pull my graph back up for a minute. So if we are thinking about increasing and decreasing, right, this is the same formula. We are looking from left to right. And what we notice is that as we start moving from left to right, these values are coming down, right? So this is decreasing in the first part, but then we get to the vertex. And if we look at what happens as we keep going, those values start to go back up. They increase, okay? So when we talk about increasing and decreasing, we're looking at things going up and down. Okay, if we quickly look at this table, we look at the values as x increases 0, 2, 4, 6. The dependent values go 37, 27, 19, 3. Those are going down. So this is a decreasing function. Okay. Let's quickly look at a graph here. Okay, when we look at a picture of a graph, we are looking at where things are going up and down. So we're going to be decreasing here. We're going to be decreasing here, but we're going to be increasing here and here. Because again, what we're doing is we're looking at what the graph does as you move from left to right, which is super important. So if the values are going down, you're decreasing. If they're going up, you're increasing, right? So this is decreasing. This part's increasing. This part is decreasing. And this part is increasing. I will tell you that on a graph, it is vitally important for our future work that you know the difference between increasing and decreasing and positive and negative. Okay, so positive values, you're above the x-axis, negative values, you're below. That is different than where you are increasing and decreasing. Okay. So try out the word problems from the horizontal intercepts and the increasing and decreasing, and then you should be good to try out some of the homework and then tackle that mini quiz for Wednesday night. Okay, on Thursday, we'll do rates of change. All right, have a good one, everybody.
I'd like to just see if, when you connect up, if you get the wired internet going.
Sorry, say it again.
I want to see when you connect up, if their wired internet is connected. We put this addition in the other day.
Oh, okay.
So you're not when you plug in the USB connector to this system.
Actually, I do, yeah.